everyone. This meeting is about Neptune, our 5 gigahertz band drone data communications use case. And the set of requirements and specifications that we're working with is called TrueFlight. This is named in order to distinguish it from earlier efforts with FlexLink, a working document that we looked at and made a lot of headway in implementing. TrueFlight is an effort to extract some requirements from that work, and then to implement or write some specifications, and then implement a prototype for demonstration. So this is a 5 gigahertz band drone data communications. This is where most of the action is in terms of drone communications. And Neptune TrueFlight requirements so far are here on the screen. The first thing that we wanted to look at, since FlexLink said it was a low latency design and stated that as part of the working document. And what we did is we took that and tried to put a number to it. And so our requirement is, a proposal is a 10 millisecond round trip delay. So we know that there are radio frequency delays. And another aspect of latency or round trip delay in telecommunications is the delay from the user perspective. So there are equipment delays, and then there's the pure RF delay. And so when we talk about a latency requirement, we need to describe which one we're talking about. So the proposal here is a 10 millisecond round trip delay. This includes everything. This is from the user perspective. There is we understand that there's what's called a glass to glass delay in the drone world, and this would be glass from the from the device that you're using, like a heads-up display or something that you're looking at on a first-person viewer display. Okay, so when we're talking about glass to glass, that tends to be what we mean. In terms of the delay for the RF side, the achievement is 4 milliseconds for like an RF delay. So when we talk about 10 millisecond round trip delay, we're talking about that's from the point of view of the user. And the 10 millisecond round trip delay is from cellular. So that's the reason for that number. And when we look at requirements, the optimizations for low latency are weighted heavier than other metrics when trade-offs are considered, meaning when we have a set of requirements, we do prioritize some requirements over others when we're trying to write our specifications. And just to back up, requirements are statements about what's required. They are usually pretty short, a sentence or two. You can see a few examples here, and we aren't as pure as some might want when we talk about reliability or latency, or things like Doppler, or if you want to broaden it and look at other products, a drop test requirement would be like, oh, the device can survive a 1 meter drop on concrete or a 3 meter drop on concrete, or you'll oftentimes see temperature or vibration requirements. So those are usually pretty simple and straightforward. The specifications are where you take the requirements and you translate them into things that you actually have to achieve in an implementation. So we're trying to follow that general thing here. When we talk about requirements, then we're trying to identify the things that are most important to us, and we've identified low latency in this communications link as the most important requirement. So the number one there, we've numbered the requirements, and that'll be important when we talk about specifications. So the number one requirement, we believe, is the round trip delay. And also then reliability. So we expect to be able to deliver bits in challenging environments. And for drones, I think we can all understand that there are some very big challenges with respect to drone communications. So one of them is multipath. So fortunately, we have some models available to us, and our requirement is that we achieve high reliability when we're in different environments. Um, with respect to drones, since they can achieve pretty fast speeds, then we do have a sort of a requirement that we can pass, and that is the high-speed train scenarios from cellular telephony. And we have a moving propagation model. That's another one that we borrowed from telephony. Um, uh, the fifth requirement has caused some controversy over Neptune's life, whether or not our data link can or should be resumed if interrupted or lost. Because we live in a world where there are uh, man-made interference and jammers, and or whether intentional or unintentional, uh, we believe that this is an important requirement, that the link can be reestablished, resumed if it's interrupted or lost. And that requirement is important to us, and has a lot of repercussions in the implementation. And then six, just to establish that the primary use case is live video and not necessarily the control link. The control link in most drones is a separate radio. So what we're focusing on is the data link that delivers, uh, data, live video with possibly some telemetry. But we're not looking at where you are flying the drone or making sure that it, you know, um, can be controlled. Also, another thing that we're not looking at is the identification. That is a third radio. If we wanted to take on these use cases or these functions, then we would explicitly say so, and now would be a good time to talk about it. So that's the introduction to the requirements. The requirement under a requirement that isn't here, that may actually be a specification, is the actual modulation, because we've kind of assumed and went with the OFDM modulation and OFDM sort of world because it has some advantages, especially when dealing with the multipath environments and the Doppler environments and essentially the data throughput delivery requirements. But it would be good. We've talked about this on Slack. It would be good to kind of go over why OFDM, because there are lots of other modulations. We have an opportunity here to experiment with other types of modulations. However, the choice for OFDM was extremely popular, and there's lots and lots of learning opportunities here. OFDM is a huge modulation used in lots of different places. Having an open source project that uses OFDM, implements it, and teaches all of the things. We're well down that path with 2 articles, one about Zadov-Chu, sequences that are used in our preamble, and another one on space frequency block coding, which is a way of adding resiliency to the signal. So since we've already kind of like put some time and energy into that, I think it would be good to at least defend our choice on OFDM and to explore other modulations that we may have overlooked when we started down this path of Neptune. Oh, and hey, Ed, greetings. Go ahead and introduce yourself.
Hi, my name is Ed Friesman. Can you hear me?
Yes.
Okay, good. Hi, my name is Ed Friesman. I'm an engineer. I'm basically focusing on digital verification of what we're doing with Neptune right now, just verifying the HDL code and trying to benchmark it, and maybe making the HDL code a little more object. I'm using System Verilog, and I'm trying to make it a little more object oriented. So as this project grows, it'll be a little more reliable. I'm reading some interesting, both for professionally in my job and other things. There's a lot of verification stuff that it's interesting because it gets swept under the rug very so often, and it's really important, and especially in places where the developers usually are responsible for testing their own stuff. I'm seeing a lot of stuff where it happens where testing just kind of gets shunted aside. it's kind of assumed it's going to be laid off to somebody who's not as good an engineer, um, which is dangerous, I think. But so anyway, I've been looking at that and just working with going through Schwarzenger's book on OFDM in general, and been looking at this specification and doing a little going back to I did an internship with NASA a while ago where I was in their systems engineering department. So I started learning the art of requirements here. And it's one thing that's interesting, I think, is that the way they always described it was the requirements were kind of divided into two things, and the two categories were dependent on the word you used. If you used shall, that was a thing this must do. Shall were all the requirements that were like, these things have to do it or it's not what we asked for. And then there are should, which are kind of objectives. Like it should have a low error rate, it should be able to do this. And so that's how in their specifications, if you look at NASA, there's the word should or shall in every single requirement. That's it's not a arbitrary thing or just a choice to vary up the English. It's actually that's how they specifically define things is like shalls are musts and shoulds are kind of we would really like, or all of the things being equal, designed to optimize or minimize this or that feature. So I personally feel OFDM is important because for the biggest reason is the requirement in all the high reliability requirements on 2, 3, and 4 are pretty much the whole reason OFDM got really popular was because one of the biggest problems any communications have is multipath propagation. The fact that if you broadcast from anywhere, it might bounce off a lake, it might bounce off a building, it might bounce off a cloud, and then you get these weird images that look like your image, but they're not at the right save, they're not at the right time, and they become very hard to filter because they're obviously at the same frequency for the most part, barring Doppler shift, and they become very difficult to deal with. And they can cause, and it really doesn't make much difference whether these things are caused by the environment and just nature and the configuration of the world, or if they're caused by jammers, like people actually actively sitting around trying to spoof what you're doing. So all these high reliability things, that's where I feel OFDM really shines. It's more compact because it does away with it uses coding to allow them to space the subcarriers much closer together, but it spreads the signal out a range of subcarriers. So, and this is where cognitive radio and adaptive signal analysis or spectrum analysis is becoming such a hot topic, because with OFDM, you have basically a set of bins you can pick and you can check which ones have the better signal to noise ratio. And with those ones, let's use higher bit encodings. So it's designed in the spec to be very adaptive right from the get-go, which is probably our best. It's definitely the most understandable way to deal with all the reliability is just an inverse of like how much interference and signal noise you're getting from the environment. And that's what OFDM was created to combat. So that's why I feel like it's valid to do OFDM. I don't know if theoretically it's been proved to be optimal, but I don't it's definitely done the best job, and it's a nice, solid, understandable approach to the problem. It doesn't have some voodoo or some kind of weird little tricks or kludges to make it happen. It's basically just saying, hey, we're just gonna go where the interference isn't. And when we have a spec that can readily adapt and move around depending on how the system environment changes. So that's why I think OFDM is valid for going forward. And honestly, it's fairly complex. So from a learning point of view, it's good. And from an implementation point of view, if we would decide we want to do something else later, almost all of them are going to be at least a little simpler, unless than what OFDM is. So sometimes it's easier to play down once you've gotten the basics done. So that's it. But I did have a couple questions based on this. One, I'm not familiar. Is the high-speed train scenario just the idea that the base station's on a high-speed train, so you're supposed to be resistant to like massive Doppler shifts, Michelle?
Yeah, it's actually the way that I understand it, and I'm sure somebody will correct me listening to this. The high-speed train scenario is generally the person with the user terminal. So a user terminal in the case of cellular telephony would be your cell phone. So imagine that you're on a high-speed train and you're passing by a station, and near the station is your base station, which is actually pretty common because infrastructure is built near infrastructure, and a lot of times, the base station would be near it or just near a train. And so you're zooming along, and will your phone still work as you pass by base stations that are going to be near the train corridors? So that's where the scenario comes from. And we can use just shifting our frame of reference. You can use this to be a stand-in for testing how well your drone um, protocol works by saying, okay, instead of the train moving with the person that's holding the base station for the user terminal for the drone, just pretend that the train is stationary and the base station zooming by you. So, or sorry, that the drone is that would, so you can flip it either way,
Okay.
depending on which way you want
Right.
to
Does
kind
it's
of like
symmetric.
say it. Yeah, it's symmetric, and there are some good established scenarios that then we say, okay, if our protocol works in a high-speed train scenario, then it will work for the higher speed drones, which can travel at 300 kilometers per hour. These are very fast drones. We don't want them to be able to outrun our protocol.
Right.
So whether it's 300 or 350, which I think the maximum, the world class drone speeds are approaching 350 kph, and we'll just say, okay, we'll just have that as a requirement that it has to work. It can't run out of gas at 100 kilometers per hour or something. And if we can achieve this standard scenario that is accepted as this, your requirement is that you have to comply with this particular scenario, then I think we're in good shape. So if it works for that, it works, this handles all of the Doppler uh, challenges that we may have that you would experience in the field using the protocol from a as a control operator.
Got it. Okay, good. And the other little point I wanted to just bring up was that on the requirement 5, the being able to resume if interrupted or lost. I mean, it's something we can try to address in our spec, but honestly, that sounds to me at least as much a networking issue,
Yeah, like a
which is like,
you mean like a higher layer, higher than
yeah, well,
just a
lower
layer?
actually, like down in the data link, or if you look at the OSI system spec, like data link is 2, physical is 1, and network is 3.
Hmm.
Like those are the lower order parts of the link specification.
Yeah,
Like, and so,
yeah, I agree. I concur. There's different places to like, for instance, in some cases you figure out that your link has been lost because you're counting um, packet sequence numbers. And if you get, or you're looking for something like a end of transmission and you don't get an end of transmission, then you know that you probably have just lost the signal, not not it hasn't really gone down. It's just been it hasn't concluded, it's been lost. Or that you have regular heartbeats, um, either hardware or software related heartbeats. And if you lose the software one, then you know that you can tell like which link is lost. The physical link might hardware is still working, the software is not. You can restart it more easily. If you lose both the software and the hardware heartbeat, you know that you're completely blocked, or and you're going to have to command things to restart. So you're true, there's lots of choices here.
yeah,
The requirement does not care where the solution lies. It's just
right,
that this link, the data link, the data transit, it can be resumed if it's interrupted or lost.
right.
In other words, we don't accept, oh, it's interrupted, shrug, oh, too bad,
Yeah,
that's
I
that's
mean,
all
I
that's
think
all the
the
requirement is saying. That specifications address the actual details or the choices that we have in the layer. And you're right, it can
right,
actually be all the way up like to the session layer, if we want.
yeah.
Um, there's
I feel like the way it's phrased, it's taking too much responsibility on what our thing is. I think it should probably be replaced like something like data link can support mobile ad hoc networks or something like that, because that's basically you basically need that net implemented on the networking side, and then just have an endpoint in your application so that it can answer and deal with that. But if the network links are gone, you don't there's nothing our little drone's going to be able to do about that, except for be able to, if there's a app hot network available, it can go find like, okay, well, here's another link that I can use, but it's up to the network to provide those links and to broadcast that they exist.
Yeah, I would say that's an implementation. That's a decision on how it does it. We
Right.
we just want to say what we want the behavior to be.
Okay. Yeah, I mean, if you look up like
I would
um
actually, if it was me
mhm,
critiquing this myself, which that's fair, is that the when you say data link,
yeah.
they're implying that it's a layer two problem. So communications or some the communications can be resumed if interrupted or lost from some sort of
Okay,
external source. Like so I would say like communications can be resumed if interrupted or lost, and that the use of the words data link is a little presumptive that it we don't want any implementation details we don't want any bias in the requirements
got it.
or as little as possible. We're not going to get away with with it being
No,
perfect, but
but okay, I like that a lot better. Like the fact that the communications can be resumed with signal loss, because that's something we are responsible for, and it's not something it will do automatically. We'll have to build it so that it can handle basically, okay, I lost my signal. What do I do? A lot of like in practice, what's happening is like with drones out in Ukraine, is that when they're losing their signal, a lot of them either have like certain options to pick from. They can either land, they can try to get back to the last point they knew that they had a valuable signal.
yeah,
They're trying obviously to make things that could still do their mission even without, like could use stuff like inertial navigation or being able to match terrain features to figure out where they are. Obviously that takes more work, but the push for autonomy is vital and ongoing for
right.
them. But yeah, okay, so yeah, just saying that we can resume, I'm down with that.
Yeah.
Yeah, that sounds like a good one. And
I've
if
written
you
that down as an action item to correct the language to where it's not presumptive about which layer, because I could
yeah,
see where that would be.
yeah,
So
because the
I'll,
data link reaches outside of our where we can things we can build, because we're not building a data network on
yeah.
it.
And
But but
before we get too far, would you like to explain, talk about the difference between verification and validation? Because since you very your summary or your introduction was really eloquent about the need for verification and validation. I mean, it doesn't work until it's tested,
right.
and I think you stated that very firmly. Maybe we should probably make clear what we mean by verification and validation.
I mean, and this is the way like I said, I'm reading a lot on this subject right now, so I'm learning a lot. Um, for me, the way I interpret it in my brain, the way I've internalized it, is that verification is making sure is like you said. I kind of view it like verification is more like checking the implementation level, like just making sure, hey, this input pushes this output out. So it's more like unit testing. Whereas I consider validation more on the level of integration testing, like saying that, do we meet requirements? Does this whole system, when put together and running, work as we wanted it to? Like what, and this validate the trick is that sometimes you can meet your specification, but you realize that didn't actually do what you thought it was going to do.
Yeah, like we didn't build the right product.
Right. Like we thought, and that's kind of where it's so important when you're developing these things to try to get somebody actually using it
Yeah.
almost as soon as you have an MVP, you kind of want somebody who's actually going to be using it, who has no stake. And that's one of the key things, it's very important that either if they're part of your company, then they have to know, like, I'm going to kind of break things and this is my job. And or they should be out of it where they don't, it's like, you gave me a product and you told me to use it and I'm going to use it. Like I send a lot of the phone apps and stuff that I make to my mom without any kind of, with the minimal amount of explanation for how it works. And if she comes back and she says, yeah, I got how to do what you asked me to do, then I feel like I've did a very good job of designing it. I feel the more I have to explain. So validation, getting back to it, is just that you're really trying to make sure that verification is a little more literal, like you're taking the letter of the law. This is what my specification said, and I did that. Validation is more saying, well, does doing that actually meet your requirements?
Yeah, does it make sense? Am I
That's the
building
way
the
I
right
think of
product?
it. There might be
Yeah.
somebody else, and if somebody else who's listening to this has an idea like, no, I think this is this. Engineers are very picky about their words, and I'd like to hear other. I'm still developing these things in my brain as far as how I'm approaching them and how I want to get them. So, any feedback where somebody says like, I don't think that's true. I have this. I'm welcome to have a discussion on it. But that's how from what I've been reading and the discussions I've had with some very smart engineers, that's how I've separated the two in my mind.
Yeah. I concur. The idea of verifying things, of verification,
Mhm,
means to me, am I building the product right?
mhm,
Did I meet did I are the specifications met? Uh, and the validation to me is am I building the right product? Did we botch something in the requirements? Did we
yeah,
build, or in the specifications? So it's like a bit, did I like you said, the letter of the law is the verification and the spirit of the law is the validation.
mhm,
And, we're responsible for both. Um, and so that's sort of why do we even split them up?
right.
Um, and it's important because you can have two different specifications that
Yeah,
meet requirements. And this is how large projects are done. Requirements are posted
cool.
and you propose specifications to meet them. You may be competing with other sets of specifications, which may come to a different conclusion if it's a complex enough system.
And unfortunately, it's vital. I mean, I don't feel that's a case for us, but in bigger, like you said, bigger and especially corporate and military organizations, which I have a little experience with. Unfortunately, there's also the problem that sometimes requirements are put in there for not the reasons of making the best system
Right.
possible. Like
Yeah.
there are some requirements out there that are just like, was this really necessary? And at
Right.
least in the military, it's a factor of the fact that every colonel wants to be a general. And the only way you get to be a general is you have your name on a lot of changes. Whether those changes were actually to the benefit of the radar, fighter, fighting vehicle, rifle, whatever, is a lot harder to tell. You'd have to know a lot more context to do it. But it's very easy for a senator to look up how many changes did this colonel implement in his system and use that as like, okay, if it's above this number, we'll promote him.
Right.
So it's just one of those systems where the system kind of perpetuates itself. Anyway, like I said, it doesn't really matter for us because I have faith in the integrity of everybody involved here, but validation, yeah, you really want. There's a lot of cases where you just got to check: is this actually a good requirement, or did we meet what did we do what we needed to do to make it better? And that's where I feel like validation. It's a different thing than verification because verification is usually fairly straightforward. Of you said to do this, I did this, and for especially lower level engineers, a lot of times you're like, that at that point they can sign off and be like, I did my job,
Right.
but validation tends to go a little higher up the food chain because it's a little more value driven judgment of, does this thing actually do what we wanted it to do in the best way possible? And sometimes that question goes back to, did we design our requirements well?
Yeah, and that's really what this meeting and the ones that we'll have, for at least a little bit is about is a validation focus. Like, for example, if I'm looking at requirement number two, what I really wanted to kind of capture was um, that the communications would work in challenging multipath environments and
Mhm.
Doppler environments, but I'm actually dragging in a particular test. So I'm saying we have to pass these tests
Right.
that and the counter argument to doing this is that I should actually come up with a more pure number. Like when I say high reliability, I need to define what reliability is. I need to say like what bit error rate we have and to define and then allow somebody to specify their specifications would include the actual test passed. So I'm kind of shortcutting the process here, even though I mean these are industry standard things, and I think it's fair to drag them in here, but it's a proper validation argument to say, hey, you're calling out these tests. And in the situation that you bring up, that you're gaming the system and gaming the requirements, what if I already knew that my pet method would comply with these particular tests? So requiring a particular test or particular scenario is has can have some negative repercussions. So your points about, validation are good. I think that we're okay. I mean, these are industry standard things, and they match the use case for drones. The high speed train scenario is very useful for us, and there's lots of test frameworks and things in like MATLAB that are already there, implementations in Python and C++ plus plus and so on, that we could just simply use without having to reinvent a wheel. So I
Right.
think this is low risk. I like it being a requirement, but I wanted it to be aired, and I wanted to like say, okay, you know, or if there's some sort of alternative way to express it, then now and the next couple of weeks would be a really good time to talk about it. Um, I mean, I think we're in good shape.
Yeah. No, I mean, I don't have any problem with the way two is written. I feel like the stuff you were like, I was thinking about that. Like, if you actually wanted to design a test for two, like a lot of times I see those kind of tests that you're talking about, those are in the specification. Like specification just isn't just how you're going to implement it. A lot of times, if you actually want them, like, because that's where the verification step is like they tries to put numbers to something that's a little higher level in the requirements. So like high
Yeah.
reliability, like you say, you can phrase that in terms of like, I want such and such a bit error rate when there's such and such a maximum Doppler shift, when there's such and such a signal noise ratio over such and such a range, although you can put those things in. If the like one thing that I think maybe should be put in here is the one thing I think should be probably added here is like some kind of range requirement.
Oh, yeah,
How
that's a
long,
good
at what
point.
distance do we expect this thing to work at?
That's
And
yeah.
mm,
Yeah, that's a
so
really that's a really good point. I think that's a it's a big omission.
yeah, and a power requirement.
Yeah.
Like how much power is this thing expected to require? Because at NASA, and I hate to sound like I'm such a name dropper, but but it taught me so much being there. I learned so much on systems engineering from those guys. And the thing is like power for them, power dominates everything because the heaviest thing in your thing is usually your battery or your power supply, and weight really, it's they say power dominates everything, but it's really weight. You're just in space, you're just everything. The lighter you can make it, the cheaper by far everything gets, because it's just heavier it's harder and harder to put a heavier and heavier thing into orbit and to get it to Jupiter or Mars or wherever you want it to go.
Yeah.
And that's also very a big factor with us with UAVs is that I guarantee you every single person who wants to use this is going to be like, if we can even get 20% power savings or 30% power savings, that will matter a lot in terms of whether people decide this can work for our application or not. So I would say like power and range are two things we should probably put in here at some degree, even if we don't know exactly what it should be. And those you can kind of put numbers on pretty easily. It's pretty
Yeah.
easy to say, make a requirement saying this shall not use more than 400 milliwatts for a station or whatever. You might have to adjust it, but you can throw a number in there. But like for things like reliability, like one engineer I knew called them the illities. Like he classified all of like
Yeah.
connectivity, testability, he just called it, which I thought was a funny way to phrase it, but it stuck. And it's like, so he's like, those can be kind of a little more up. And then in the specification, we can start talking about specifics like bit error rate per frequency bin and stuff like that. And you can get a little more down because also the specification, it's kind of more like since where the specification includes OFDM, that's going to determine, oh, okay, well, we're going to have a bunch of signal carriers and you got to look at the bit. And okay, so are we going to do like LDPC encoding or ZF2, how
Right.
are we going to encode it? Because those
Right.
can help, or forward error correction obviously can help reliability when we don't without affect well we can still leave us free to design other aspects of the spec,
Yeah,
but
and
you got to implement.
it directly affects all the other things
Yeah.
too. So,
So
yeah, okay. No, that clears things up. That makes sense.
yeah.
And
So
yeah, if we go ahead and propose something, then we can get feedback. That's and that's super important and valuable right now. Like, the range requirements, and so size, weight, and power swap is since it's a vehicle.
Yeah.
Size, weight, and power is obviously
Well,
important.
especially a flying vehicle. It's
Yes,
just like
especially
it's
a
like
flying vehicle. Yeah, and anything
that
like anything with latency, to reduce the latency means that you can turn off the battery.
mhm,
And, even if you have some sort of slow, eh, that one of the discussions that we had with FlexLink was it has a relatively slow subcarrier spacing. And I was like, okay, well, so we can save all of this time. And it was interesting to me that the response was, well, who cares? Since the subcarrier spacing means that things come around ever so often, your symbol comes around reliably. Well, who cares if you have low latency in between these beacons or not beacons, but the boundaries. And I
mhm,
said, well, okay, so then you could save battery. And on a vehicle that's battery powered, you want to shut things down as often as you possibly can. And it was interesting to me that that didn't get any traction. And so so I'm looking for things like that to just latency matters even when you have a fixed framework for your symbol coming around that you get
well,
to
yeah.
turn things off and save battery.
Yeah. Well, I mean, ask any FPV drone driver. Like latency is critical because if a couple seconds of delay is enough to get in return from something they can pilot, especially at the higher speeds, to something that's going to crash.
Yeah.
So it's like it's not just we can't just look at it like this is a data link that's just for moving buckets of data in between drones. A lot of this is going to be used for helping the operators operate.
Yeah,
And
I mean, if we
so
wanted if we wanted this the first person view or the live video to be consumed by, say, um some sort of computer vision,
yeah,
then you can't afford to lose any extra milliseconds along the way because the those algorithms for for computer vision are not generally very low latency. So
yeah,
you can't deliver it. Yeah, if anything that we save will
yeah.
pull that into being more and more possible.
Well, even
So
without any video signal processing, just operation.
yeah,
Just like how long it takes for a video image from a clean video stream from the camera to get to the operator. If that's above a certain amount, then that guy's going to crash it.
yeah,
It's like you don't need a lot of those things are not. I've tried my little drone's very slow and not very far. So, but I can. It's easy. I've seen racers and it's like I forget what they said, but it's in the milliseconds. Like if it's much more than a couple milliseconds, then then like I can't fly. I can't race this thing.
yeah. We
And and that's like with no signal processing, nothing. That's just getting the HD video from from the drone to the cameras to the operator screen.
Right. Yeah, if we want to look at that, then we know what we're up against
Mhm.
in the market. So 20 to 40 milliseconds of complete delay, like the operator is sitting there looking at a screen with their fingers, on the controls, and you want to minimize that number.
Yes.
So what's under our control in a communications link is the RF delay. There's other delays in the equipment, but our, our round trip delay, if we were going to propose 10 millisecond round trip delay for the RF side, the feedback that I got for this requirement so far is that it actually should be closer to 4
Right.
milliseconds round trip delay and not
There
10.
could be other things contributing that we have no control over.
True. So if we can then say, okay, our we need to be 4 milliseconds or preferably lower. Like if we really want to make a contribution, then this is our most important number.
Yeah.
And that everything else is, yes, it's important, but this particular number gets weighted the heaviest. And this requirement, the 10 milliseconds, may not be good enough. So I was looking at round trip delay as like a real round trip delay, like as if it was the operator was this is what is delivered to the no, that's not really true. So it's unlike cellular telephony where your ear is actually hearing the round trip delay pretty much. And if there's other delays in the equipment, and they tend to be larger than other consumer electronics, then we need to actually specify both. Like here's our delivered RF delay, and here's our assumptions about the round trip delay. We need to actually work that into the requirements somehow.
And I think this is a perfect example of the difference between verification and validation. This is definitely a validation thing because there's some information we're going to have to get from people who operate these things practically.
Yeah.
So we're going to need some feedback. How do you test this? What do you really need for this to be functional? And
Right.
it's going to be a bit of iteration as far as like, okay, we got something here. Can you try it on your system? And is it good enough? And is it, and so, and because there are people who are asking this question a lot and dealing with it. So it's like, and since we want them to use this, they're stakeholders in what we're doing here, even if they don't really feel like they are.
Right.
They got some interest in this, and they got some things to, I'm sure they'll have some things to say about, well, here's how we test it, and here's what the number, here's what we consider necessary to do our job. So this
Right.
is one of those requirements where it's like, definitely it's not in the specification realm, it's in the requirements realm, but it's something that validation will have to address.
Yeah. So I think that the requirement number one needs some definitions. Like the round trip delay to me was RF delay. 10 milliseconds was pretty generous, but I thought it was definitely beating the 20 to 40 millisecond round trip delay that I was quoted. But we're talking about two different things. So the to me 10 millisecond round trip delay is the RF delay, and the 20 to 40 is glass to glass. And I'm like, oh, okay, these are two different things. And then the feedback that the RF needs to be lowered and it needs to be like 4 milliseconds or lower was really good feedback. So there's two things that need to happen, I think, with requirement one is that we need to define our terms and that this number actually needs to be lower. And we can go lower because we have access to lots and lots of really good work. Both requirement side and implementation side from cellular telephony, we can actually get this round trip delay pretty low. And because we don't have a lot of the functions or overhead, there's a lot of things we don't have to do with our particular link that do have to be done in, say, cellular telephony. We can borrow the things that reduce the latency because lower latency was like a big focus of 5G. So we can take the things in 5G that reduced round trip delay, that reduced latency. We can take those things and we don't have to also pay or do the things um, that increase delay. So there's lots of things we can dump and there's things that we can adopt. And I think we can get down lower than 4, but 4 milliseconds may actually be the number. So two things, replace the 10 with 4 and define our terms better.
Right.
That the round trip delay, we're focusing on the RF round trip delay and that the equipment delays are going to be additional. Like if there's any processing or UI or whatever, um, that those are not that's not what we're talking about here. Yes, we may deliver a prototype that has additional delays in it because we're using off-the-shelf gear to show stuff on a screen or provide you some sort of some sort of control panel or board. Uh, but those those things are not that would be another project. That would be that's not part of the requirements.
Yeah, two to six is good. Yeah, one definitely I feel needs some iteration. And if we can add like a power and a maximum range kind of
Yeah,
requirement, then I think those are the three big action items on this right now.
yeah, I've got it. I've got it written down, and part of the publishing of this meeting will be to include that as the sort of the here's the action items that came out of it.
Yeah. No, that sounds good. I mean, yeah, it's a process. It's a
It
process,
is.
and but it's really important, I feel, to do this kind of work that, getting this right is important.
Yeah,
If you
it
do this
is.
right, a lot of future pain is put off. If you do it wrong, it ends up in recriminations and people claiming you bad intentions and other things. And that's the sad part, is that so many of these things start off with great intentions all around. Nobody wanted to make the Apple III. Nobody wanted to make a shitty product. But it's just you got to be clear about what you want this thing to be. And it can't be everything. It's got to be one thing.
Yeah, well said. So I guess would be good to talk about like, okay, so we have these requirements and we are spending time improving them and we'll revise them and then put them out again. And yes, it's an iterative process. At some point, we'll call it. We'll say, okay, we're good.
Mm,
And then, but there's nothing stopping us from talking about, in sort of in concert with this to talk about some potential specifications. And so there are some for discussion. So when we talk about specifications, we derive them from the requirements, like you introduced, like you explained here, that this is like how we implement the things that we have said we require. The first sort of requirement, and this, and you can see I'm already assuming OFDM. So actually, the first requirement, the zeroth requirement, maybe,
mhm.
would be OFDM meets our needs. So I think I'm going to put that as the fourth action item, that
Okay.
to go ahead and say we're going to specify OFDM, because as you can see, I just kind of assumed. And you don't want to do that. When we do specifications, we really want to go ahead and say, okay, OFDM meets the requirements. That's the thing that is the best suited for it. And be open to somebody else coming along and saying, well, what about blah, blah, blah? Okay.
Right.
But we'll just go ahead and so I have the fourth action item is no, back up and say OFDM is what we're talking about.
Yeah.
When we talk
Sometimes
about
sometimes
OFD,
the best requirement is just like the old theater adage. It's like, well, do something, and then we
right.
can change it.
Yeah. Or
So,
never,
like, if somebody
or
comes up with a great argument to use some other scheme or to use maybe a slightly, there are other flavors of OFDM that are kind of, you could argue they're the same thing or but they're, if somebody's got an argument for it, then I think we should definitely be, I mean, as a group, we're the Open Research Institute, so should we open to it? And it's just
right.
like, let's
Yeah. And
listen
those,
to it, but you got to make
yes.
a case.
Yeah, you do. You have to make a case and you have to prove through your structure of your specifications and requirements that you're open to other specifications. And I didn't do that here. So what I'd like to do is I'm going to back up and establish that okay, here this in the specifications, we think that OFDM meets the requirements. And now we're going to list our specifications for meeting the requirements. Okay, so that's
I second that
there.
motion.
Yeah, there's
Any
some
thirds?
improvements that need to be made here. And so what you're seeing on the screen is like, okay, here's the first kind of cut of a set of specifications. And with OFDM, one of the first things that you need to deal with is the subcarrier spacing and the signal bandwidth. So
Yes.
that's why we have this discussion here.
Yeah.
And the subcarrier spacing here is 60 kilohertz. It's not the 13 or 12 or 15 or 20. We had a number of different numbers for FlexLink, and I accepted the FlexLink specification and then started working on it, and that's how I came to learn about OFDM, because
Right.
I'd never had a chance to work on it with any seriousness before.
Right.
And one of the things that kept coming cropping up was the subcarrier spacing of 15 kilohertz is very, very common. That is, LTE, it's been around for a while. But when you start looking at the higher frequencies, 5, 10, 24, 47 is what we are allowed to and actively use, that the sub-carrier spacing of 15 kilohertz is a little a little low. And when I asked about this, it didn't go anywhere because there was no requirements for FlexLink. It was simply it was delivered as a specification. And so when I started asking, like, if we're going to do 5 gig, why is, this seems like a little on the low side. And the reason that I asked about that is because it's like, well, okay, your choice of subcarrier spacing actually is somewhat frequency dependent, and that
Hmm.
and also it directly affects the latency. So
Yeah.
a 60 kilohertz subcarrier spacing is the one that people use for 5 gigahertz and above,
Right.
and 15 is a multiple of 60, and that's why the numerology works out. So
Okay.
when you design a system for 15, you can actually uh, you know it's a compromise, but 15 and multiples of 15 are what people look at. We really do want to use 60 kilohertz. That was my sort of like, okay, I came back and I said, look, the specification is great, but like 15 or some other number, because it never was 15, it was either 20 or some other number. And if it was 15, I could see a path forward, but why not use essentially a faster subcarrier spacing? Because if low latency really is the most important thing, this is the quickest, easiest way to give us better latency numbers.
Yeah.
And so those conversations didn't go anywhere. And so that's sort of, I said, okay, then we need to go ahead and extract the requirements from the specification. So if you can't give them to me, if there isn't a document that already has them, then we need to do the exercise of going ahead and extracting them so that all of these numbers in the spec make sense. And
Right.
when that didn't go anywhere, it's like, okay, let's go ahead and back up and do requirements. So 60 kilohertz is the proposal. This is very common, used at at higher frequencies. The frequency range, the way that frequency ranges are split up in cellular, 60 kilohertz is a very, very common choice. I don't think that we'll go wrong here. That's why it's proposed as a specification that meets the requirement of delivering low latency communications at 5 gig and above. And there's some citations here for some of the, some papers that are widely cited that talk about the results and mention the fact that the 15 kilohertz is so common, 60 is a multiple of, so that it gives us some flexibility with some numerology uh, used in 5G, LTE, 6G. So that's why it's there. So I'm comfortable with 60 kilohertz sub-carrier spacing. The numbers work out. It's achievable with the FPGA dev stations we have, and that leads directly into the signal bandwidths proposed for the chip that was picked for to support FlexLink. The maximum transmit bandwidth is 40 megahertz. It's designed for mobile devices. It's the ADRV 9002. I'm really happy with it. It's paired up with the ZCU 102, which is an UltraScale Plus Xilinx chip, very capable. We can do all sorts of amazing things with this combo in the lab. I'd really like to see 100 megahertz to deliver the sorts of throughput that we would like to see for first person video. We're limited though with 40 megahertz is our biggest. That's still really good. So the
Mhm.
proposal was, let's say that we have a baseline design of 40 megahertz so that we can demo it in the lab and that we make sure that our protocol will also deliver 100.
Okay.
And there's been some feedback about that. I think from Matthew. Um, but those two numbers are picked there that we're picking two. We could just pick one and just say 40, but then we'd be
Yeah.
admitting that we're tied to the equipment that we just happen to have in the lab.
Yeah.
And 100 megahertz actually works, and we can transmit a 100 megahertz wide signal on 5 gigahertz.
Right.
Yeah, if we use the licensed amateur radio allocation. And in
Right.
reading, I found out that drones basically totally use the licensed amateur radio allocation. It seems to me that they are just simply, and they don't care about the band plan. I did, so I wrote like where in the band can you go, which causes the least amount of damage to amateur communications. None of the commercial folks have paid any attention to this, and that explains a lot
Yeah.
about weird,
Yeah.
interference
Why my
issues.
radios keep failing.
Right. It explains a lot, but the counter argument is that, there's a lot more drone companies and drones out there droning around than there are experimental ad hoc or mesh networks on 5 gig or 5 gigahertz point-to-point communication, which can operate with a lot more gain and directivity. So I think we're in good shape. We can actually operate almost wherever we want. I think we should go ahead and follow what the other drone folks are doing. um, we can be a little kinder, but with a minor change. And that's laid out in this specification two discussion.
Yeah.
I
Moore's
but
law is
I
a thing. So yeah, eventually 100 megahertz will be possible. The hardware will support it.
Yeah,
That's
we'd have to pick a different radio chip, but that's fine. But
yeah.
if we say okay, 40 megahertz, let's get the demo, let's
Yeah.
get the prototype working at 40 megahertz, then we can use the equipment we've already purchased
Yep.
and just make sure that we know what we're doing with respect to the protocol. And you know what? The so in talking about this issue, there I found there actually is some really cool stuff that you can do with OFDM. So when we talk about signal bandwidths and specs that support either low latency and also reliability and things like that, there's some really neat things you can do with OFDM. You can add subcarriers when making hay is good. When conditions are great, you can sprawl out and add sub data subcarriers. And then when things are not so great, you can pull back. And in other words, we talked about adaptive coding and modulation with respect to our DVB-S2 work, where depending on the signal noise ratio, you modify your coding and your modulation in order to just ride the capacity curve, right? So that's
Right.
how it's done, and it's really neat. It does require some complexity and some agility, but
Mhm.
you change your coding and your modulation in order to take advantage of better or worse, channel conditions to deliver the most amount of bits possible. Now, that means your symbol rate stays the same. And in our case, our symbol rate is staying the same. It's just that how many subcarriers do you add? So our core, like next to our essentially the center frequency, all of the stuff that you absolutely have to have in order to identify the signal, to find your signal, to stay connected, all of that stuff needs to be fairly close to the center frequency. Maybe that's our 40 megahertz. But in the case where we have the ability, whether capacity from the channel itself or capacity because you have a better radio chip, that you just sprawl out and you're able to go to 100 megahertz. That may be what we want to do in order to allow it to be adaptive, that it's
Yeah.
something that your hardware can take advantage of, and it's in the protocol.
Right.
Um, so that's an opportunity for us to implement something that has only been implemented by the most advanced networks, and then teach that way of doing things in an open source way. Like this is a very accessible way to learn about a fairly advanced technique, that you have bandwidth agility and that the protocol allows it. And here is why. You have the must-have stuff within this bandwidth, but you have this extra capacity that you can take advantage of, and that's negotiated between terminals. So that would be one way to defeat it.
Instead, it's basically like, I mean, in one way, theoretically, you could reduce it to the knapsack problem, except instead of having one knapsack, you got a bunch,
Yeah,
which is maybe I imagine is much more complicated, but it gives us the ability. We're basically figuring out where can we store, which bins do we want to store our signal in, and to
right,
get the bandwidth that we and the latency that we require. So yeah, I mean, these are all good. Obviously, like if you have more bandwidth, like if you have 100 megahertz to hide in as opposed to 40, there are a lot more things you can dodge, because like you can dodge like
right,
Doppler shifts and other things like that that might force you to spread out. If you have
right,
100 megahertz, you're more likely to be able to, that gives you a bigger velocity range you can cover. That gives you a lot. It gives you a lot of things to hide. So if you have some specification that works at 40, it should work at 100 if you have the hardware. So yeah, I mean, it's definitely something we'd like, but we can do 40 now. So it's kind of like the old general patent thing of a good plan now is better than a perfect plan 2 weeks
right.
from now.
Yeah,
So the good plan is like 40 megahertz. When 100 megahertz becomes readily available, I think we should be able to shift the work we're doing to include that pretty
right.
easily. I
Yeah,
think
and
it's good. I
you
like
can
it.
and
Sounds
then
good.
at the very bottom was of this signal bandwidth section was two action items to gather feedback from the band planners about the proposed signal placement, which I did, and lots of different interesting stories there. But in general, we're good. So
Are we
we
going to
have
itemize that or that information or anything or
I'm
publish it?
yeah,
Or
it was a remarkable set of conversations with some people. Some of the amateur radio band planners would really like to kick off all of the people using drones because they view them as pests, and then other people who view them as like a significant players that should be supported, and that the band plan should adapt to the realities of who's using the band. What it boiled down to was we're good as long as we avoid um, I mean, if we go ahead and avoid like the satellite and weak signal and EME people, then we have only 69, 70 megahertz. But if we only avoid the satellite subbands, then we have 160.
okay.
Um, and so like it's basically it's up to us. And these band plans are voluntary. There's no regulatory issue here. The only regulatory issue is where can you legally transmit at the power levels that we want? And the entire band's open to us. it's a question of how collegial and do we want to be? How responsible do we want to be to the other people that actually use the band? And we can see that there's a huge range of of behaviors with most of the drone companies not really paying any attention to the voluntary ban plans and only looking at the regulatory allocation. So we can take that approach, or we can avoid the the users that are most sensitive, which include ourselves. Our satellite
Right.
uplink is in 5 GHz for high area. So we're pretty sure though that we can, this is a case where you have a dish and you're pointing to a satellite and your gain and your fairly narrowband signal uplink is there. Drones are going to be no problem for us. So using that sort of knowledge, then I think we're really good in the allocations and the bands that they've picked, that up to 100 megahertz isn't going to cause any trouble. And yeah, like you said, it the broader the bandwidth, then the more resilient the signal is to a lot of different conditions. So I did do that, and I conscripted a couple of other people to also go ask, just to make sure, to double check, and we all got about the same results. So that was good. And then I had a second action item to go ahead and enumerate the expected throughput for like 100 megahertz and also 40 and whatever. And that got a little hard. OFDM throughput calculations, with the
I'm sorry,
more,
Michelle.
yeah.
I'm sorry, I didn't mean to interrupt you. But I just unfortunately I do have to go. This went really fast. And unfortunately,
No,
I
totally
got a nine
understand.
o'clock. I have a 9 o'clock meeting, and
Understand.
I
Yeah.
gotta
Okay.
get going. So if you gotta keep recording, please do. Everybody else who's gonna listen to this, I hope this was helpful. But yeah, unfortunately I gotta bounce. I'm really
Okay.
sorry.
Yeah, I'll close with this point. The expected throughput calculations are actually much more
Sure.
complicated than I expected. I found a couple of calculators. Expect 5 to 10% overhead. Will probably be more closer to 5. And that's it. Okay, so as you can see, this is sort of how we're working through the requirements and the specifications, and our goal is to have something that works over the air in our lab with the parts that we currently have. That's an ADRV 9002, a nice RFIC designed for mobile applications, and a ZCU 102, which is the Ultra Scale Plus from Xilinx. Um, Boards eventually will be laid out and made, and demos as soon as possible will be done. We're hoping to have some demonstrations at DEF CON in August of 2024 in the RF Village. All right, thank you so much to Ed and all the rest of you that are working on this and enabling very ambitious things to happen. And we'll see you soon.